proud to introduce our speaker from IBM today. Damiaan Zwietering is a Python developer who's an architect, he's a consultant, he's an innovator, and he's going to help us to understand and make a little bit more sense of measures. So Damiaan, thank you so much for joining us. Welcome to the community.
Well, thank you. Yeah, it's great to be here. Today I'm going to really dive into some technology. So it might be very technical at times, but it's also a personal story. So you can ask me questions about anything. I regularly do after a series of these talks. I even do an Ask Me Anything. And wondering about the kind of questions that come up. And one of the questions that comes up a lot is from people who are starting out in data science. They're interested in data. They're thinking, hey, this is a very interesting area to work in. And they, to my surprise, they sometimes come to me and they say, I've done the Coursera stuff and I've done all the exercises and I think I know my way around. I can explain the difference between supervised and unsupervised learning, and I know a couple of the definitions. But now what? And I'm always surprised by that kind of question where I say, now what? Well, now what? Just find a subject, get our data on it, and start analyzing it. But that always seems to be some kind of hurdle in the heads of people that they don't really start out for themselves. So I'm very happy to hear Bente's story telling us just if you have an idea and you think we should go in this direction and we can change something for the good. My take would then be, as a data scientist, start gathering the data, find out what's going on, and see what you can do, and explain or what kind of insights you can gather there. So it always seems to be a bit of a struggle to really get started in stuff like this, and for me, it was a little bit of a struggle to go open with this because I used to work at customer projects. A lot of them were very hush-hush and we can't talk about this and no press release, and we're just going to build this and it's going to run in the background and don't tell anybody more or less. But these past 4 years, I've been working as a developer advocate. So I've been mainly working with open source. And since last year, I've also open sourced all my work. I just said, okay, I'm just going to start out on Git. Everybody can use it. Everybody can look at it and reuse it. No problem with me. My job right now is just to inspire people to get going with this technology. And that seems to be the biggest problem, to my surprise, to get going. Just start out, get that data and start working with it. So there's going to be a lot of that today and a lot of messy details, obviously. So I would be very interested to hear your questions. I don't know anything about the background of the people that are in the audience. Maybe they might be deeply technical, but they might also be just starting out and just interested in what's going on in this data science world. Any question is welcome. No problem. No problem for me. So I'll just be spending the coming 90 minutes more or less in showing stuff that I developed last year on analyzing COVID data. And we can go in a lot of directions. No problem for me to talk for 90 minutes, but I'd also be very happy to hear from you what your input would be or what your questions are in dealing with this kind of data. And we'll start off with the Git environment, where it all started last year. So I just, a little bit of the personal side. IBM obviously asked everyone in the organization to start working from home somewhere in March last year, I think, or early April. Same for me. Luckily, I do have a good office at home, so I was already used to working 1 or 2 days from home before I had to go full time. At the same time, my wife, who is a nurse, was already very busy at our local hospital in treating suspicious COVID patients. So she was in full isolation and the whole lot. So there was really a personal side to all this analysis stuff as well. And at the same time, I was thinking, I'm going to do workshops this year again, like as usual. So what would be an interesting subject? So that question answered itself more or less. So as a data scientist, I was thinking, can I do anything with this kind of data? That's coming in helping out what's going on and helping out society, helping out healthcare. I didn't know yet what would come out. I just started out downloading this data and starting out in working with it to see if I could make sense of it. And that's the first meaning of making sense of measures. We measure a lot. So the measures that I'm going to work with today are mainly infection measures from so daily counts of infected people in regions, countries, whatever. So that's the measure I'm working with. And the first job of a data scientist is to make sense of that. What's going on? What's happening? Can I model this in any way? Can I understand the progress of these numbers? Are they in any way related to the situation that the country is in? Can I relate it to the healthcare system or to the general health of the population? So what is going on? So the first thing is just taking in these measures and start analyzing it. And luckily I do have a lot of experience with that, so that might be that was the easy part, getting started, because I've been doing this kind of analysis work for over 25 years. I actually studied artificial intelligence. That's almost 30 years ago, when the first people started thinking about artificial intelligence. So there was a lot of theory there and very little practice. We already were pretty scared if we got a data set with 1,000 records from customers, for example. That was already a big deal at the time, while now on my laptop I can easily process millions of records coming in, and so there's a lot more that you can do in the meantime. And I got quite some experience in dealing with data. So everything is that I show you today is freely available. So you can simply go to this GitLab page that I'm using here. Yeah, as you can see, I've been pretty busy quite last year. So these are my submissions to my own projects last year. So it really took off in November when I started automating stuff and doing automated submissions. So that from then on, there's a lot of material. Most of it is still up to date. I'll show you a couple of stuff that's on maps as well, which are not fully automatically updated because I'm still looking at what's going on. So I always check more or less every day what's going on and is what I'm mapping still correct. So there will be quite some updates. So you can even see that. I'll just refresh this page to get the timings right. You can see that 5 hours ago I did the last change to this project. So it's still very much up to date. So please, if you want to contribute or if you have questions about this, have a look. So yeah, all open source, so it's all available in the main project, which is called Corona. Yeah, I didn't have that much inspiration at the time. You will be introduced in my terrible naming schemes afterward, but I started off just calling it Corona. There's already a README after a while. It took me, I think, 6 months to start documenting this stuff. But lucky for you, as somebody who looks at this first, we'll have some documentation. There's lots of links to useful stuff, and probably you'll find your way around here. But have a look for yourself. So this is the main project, and I did a lot of workshops obviously last year. So there's a separate folder here which is mentioned here under the workshop heading, where there's lots of stuff with descriptions ready for you to use. So if you want to start redoing these analysis for yourself as an experience, it should be pretty easy. You just start out from this workshop folder, and there's a pretty extensive README there. With pointers on where to run this stuff, how you can run it in the IBM cloud if you don't have your own analysis environment. On the other hand, it's pretty easy to run. Most of this stuff just runs in a plain Python Jupyter Notebook installation. There's not much special stuff needed. And the code that does need special stuff will most of the time install it by itself. Which can go wrong in all kinds of terrible ways, obviously, when you start doing that locally. But you should get up and running, at least with the first notebooks, pretty easily. So I'll show you examples of that. So workshop material, I'll just invite you to go through here for yourself. The one that we will concentrate on today is this one, getting to know the data. So that's one which I will use to show you what kind of data we're looking at and how I'm looking at that kind of data as an experienced data scientist. Maybe that's even more interesting. We will then also have a look at relating outbreak severity to country measures, which is also an interesting project. And that is actually the second meaning of making sense of measures. So the first one is the measures that come out of the field, like infection figures, even deceased figures, stuff like that, hospitalizations, all that kind of measures, making sense of that. And the second one is measures in the meaning of what measures does a country take to flatten the curve, basically. That's the first thing I started looking at. So if somebody tells me from the government, we need to flatten this curve, then I, as a data scientist, react in saying, okay, then what is this curve and how do you flatten it? And can you measure that in any way from the figures? And how do the measures that a country takes, like lockdowns or health measures or everything, do they actually flatten the curve? What happens to the curve when you take those measures? So that is actually the second meaning of making sense of measures. So it's actually first looking at the details and then looking at how do we influence those details and can we influence them and what's the difference between countries and stuff like that. So that is all available from here. So you get the right pointers. There's lots of links here. There's lots of stuff to look at. There's even some suggestions for things to explore for yourself if you got through all this introduction stuff and you want to see what can I add to this. So there's quite some example stuff here, and yeah, for the coming hour I will take you through the first steps to see how you can get started with this stuff. Later on I'll be asking you for your country. Because I will start out most of the analyses with using the Netherlands as an example, because I live in the Netherlands. But I can. This is all running live, all this code. So if you say, okay, show me the figures for the UK, I'll be glad to do, and we'll see what comes out. There might be big surprises for me as well, because I don't look at every country every day. But please shout out, and we can have a look at your country and try to make sense of what's going on there. So yeah, shout out your country if you want to look at it, and I'll be asking for that as well later on. So the first thing as a data scientist is, yeah, looking for data. That can take a long time. I've had projects where we discussed the kind of data that we would like to use from an organization, and it took us 9 months to gather the data before we could even start analyzing it. I didn't want to wait 9 months, so I started looking for data sources, open data sources that already provided infection and disease figures right from the start. So the first, one of the first I found out is the EU CDC. Unluckily for me, they stopped providing daily figures somewhere in December last year. But until December, so most of last year, I used the daily figures from EU CDC. They are worldwide infection figures. So basically, what I do is I use 3 columns that just say, okay, I've got this date, I've got this number of infected people for this region. So basically, I start out with as little data as possible, which may sound strange. We always hear from data scientists, yeah, we need as much data as possible to make sense of all this stuff. I always start the other way around. I start with as little data as possible for 2 reasons. One of them is, I think you should add data step by step. So first make sense of the basic stuff. And when you don't understand anything of that, you look for data to explain that, and then you start expanding. So that's step by step building out your data set, but analyzing all the time, not first gathering everything and then start analyzing. That's the first reason. And the second reason is usually, and that is very important in this case, I wanted to only use data that I had available for as many countries as possible. And the reason for that is, if you're trying to make sense of, for example, the progress of a disease, and you have data from very different circumstances, and you find something in your analysis that is similar, for example, to Japan and Iceland and Argentina, let's just take 3 countries, which are wide apart and totally different circumstances. So if you find something that is similar between countries like Japan and Iceland and Argentina, then it's probably a basic truth. So I look for data from as many different circumstances as I can get, because if you then find something similar, it's probably a general truth about disease outbreaks. So that is, and that also, I had to restrain myself a lot in the kind of data that I could use, because, yeah, I mean, all the details about population health and hospitalizations and stuff like that is just not available for many countries in the world. And if you concentrate on all the rich data that is available for some countries, you will find that you have a very strong bias to developed Western countries, because that's where all the data is available. So if you then find out something that can help you in finding the disease, it will probably only count for that kind of countries. You won't be able to use that in Africa or in whatever region you're looking at. So there was also something to take out as much of the bias as I could. I used as little data as possible, which might sound strange, but that is how I usually start out in projects like this. Right, so EU CDC data. So yeah, most of these notebooks, as you have any experience with these notebooks, this is just running live Python code. It's a very easy way to interactively run this code. Most of these notebooks download their own data. So in the beginning, there will be some descriptions. I haven't documented them all as properly as this one. But usually the notebook starts out with downloading its own data. So this is first statement, which is just a wget, which is the operating system statement to download a file. So it just downloads the data, and it downloads the Excel in this case. I tend to work with open text formats, but especially in the beginning, the text formats that I downloaded from EUCDC were very unreliable. So there should be commas in between the numbers, but sometimes there were suddenly no commas and there were quotes where they shouldn't be and stuff like that. So I started using with the Excel file that they have available because it was just more a constant data format, more reliable. So that is, but there's lots of other examples in other notebooks using other types of files as well. So here the usual analysis libraries. Pandas is a very useful library when you want to work with a lot of data. I always say the best thing about Pandas is if you have data in a data frame, you can simply do one statement and change all the data. So if you simply divide your whole data frame by 2, then every number in the data frame will be divided by 2. So it makes it very easy to change around and adapt large amounts of data. That's what Pandas does for you, but it does a lot more, obviously. But and NumPy is the basic Python library for numeric calculations. So there's quite some calculations going on. So that's where I use these libraries for. Well, then it's just a question of reading this Excel file. Luckily, there's just a Pandas function that you simply give the Excel file, and it will load it into Python for you. So that's pretty easy. If you're experienced with this stuff, it will be pretty obvious for you. And the first look at the data, and here you see the kind of data that I got in the beginning, and that you can directly use then from your code. So the basic 3 columns that I was looking for are there. So it's date reported, which is the date. There's a number of cases. There's also a number of deaths for that region, and there's a country in this case because it is country level data. And I started using this GeoID right from the start because that's a unique identifier for countries. So I got to learn a lot of these 2-letter abbreviations for countries. And then suddenly halfway I had to change to a data set where they used the 3 letters. But so yeah, that's the usual frustration of being a data scientist, that your coding system somewhere goes wrong. Anyway, a lot of these codes there. So this is just opening the data set, and yeah, then right away the problems start. Well, if you can call them problems, you can whatever you want to call them. For example, there's a country in the data set that's called Namibia, which is a country in Africa, and the GeoID of that country is NA. And by default, Python will understand something that is called NA as not applicable. So it's refused to read in the data from Namibia in the first run. That's the usual stuff that you get when you start using code importing that data. I got all kinds of weird messages that there were countries with no GeoID, and I thought, how is that possible? Because every country has a GeoID. But then I found out, and that's the first 3 hours of analysis. Then I found out that the data for Namibia was being ignored. That's the usual stuff. There's always stuff in the data that isn't like you expected, or your code behaves like you don't expect it. So there's always stuff like that going on. So that's for example why there is why I say in this Excel import that I don't want to use the default NA handling, because then my whole country gets ignored. And there's lots of stories there, but what it means is always look at your data, also in detail. Just open the file yourself in an editor, have a look at it. If all the commas are in the correct places, if the quotes are there, and even if the codes are properly used. But if you're a beginner, this can be pretty frustrating because if you if you just ignore stuff like this, your code will simply not run. Because one of the weird things is that if you then convert this to columns, Pandas will start throwing errors and stuff. So it's as a beginner, it can be quite frustrating to open your first data set. And then I started understanding a little bit more about this hesitation of people to really start out using raw data for themselves. I always say if you don't like the puzzling, if you don't like those puzzles, like figuring out what's really going on, you might not get very happy as a data scientist, because that is where you spend a lot of time. And then there's always checks. So there's a lot of code in this notebook that is just basic checking if everything's correct. So don't ever assume anything about your data set. Always check, always do the counts. So this just does a count, and it tells you if all the columns are filled. And you can see that some of the columns have missing data. So I don't have population data, for example, for all of the countries, but at least the columns that I want to use, the date rep, the cases, and the GeoID, they all are fully available. So all those columns are filled. There's always a lot of checks and balances going on where you start working with data. So don't ignore that. Don't just load the data and start running your first model. It probably won't work, and the worst thing is you won't understand why it doesn't work. So that is the basic stuff that's going on. And this is another of those checks. So here I just check if I have any countries left with a missing GeoID. So I look for countries with where the GeoID is not available. And I get an empty result. So there's one of those checks. You'll see a lot of those in notebooks that you see from me, where there's just these short lines of codes with no result, and they are my checks. There should be no result because there should be no country with a missing GeoID. So that's one of the things I learned in these years. Always check, recheck, triple check. It's always going on. So I won't bother you too much with all those checks from now on. Be sure that they are there. And then it's just a matter of what I had was what I always call this long narrow data set, just 3 columns, and for all the countries are in the rows basically, and that is a pretty hard format to analyze. I mean, you can do all your queries on there, but it's not as easy to access. So the first thing I do is I do a pivot, which basically does the same as for when you're using with Excel, just a pivot of that data set. So that I get 2 slices now, one with all the case data and one with all the death data, which is on the right. Every row in the data set is now a date, and every country is a column. And then you can already start understanding that it's pretty easy to start analyzing here, because now you can simply select this column and you have all the data for, in this case, AD, which is Andorra, very small country in Europe. So, for example, this is Arab Emirates, Afghanistan, and you can already see that the data is there for these countries. This is a format where you can start analyzing basically. So you've done all the checks and balances, and you've now got something that you can start analyzing. So the next thing is looking at what kind of data do I have? Is there something weird going on? That's always something that I do, which you can very easily do with a describe here. So, for example, you can see for Andorra at that time, this is not the most current data. I had 276 data points with a mean of 26. So I'm looking at the cases here. So already there's some data coming up where you can say, okay, for the period that I'm looking at, Andorra had on average just over 26 cases, 26 infections per day. That's what's going on here. So you see already quite some differences. For example, if you look at Afghanistan, but then Afghanistan is a much larger country and stuff like that. So you can start digging in from here. So basically what you do is you get your data in a format where you can start asking questions to the data. That is what I'm always trying to do here. So already some figures here. There's also a minimum and a maximum. So there's quite some days where there were no cases reported. And for example, Andorra had 299 infections on one day as the largest figure. So that's already interesting, but at this point, you're usually looking at, is there anything weird going on here? So if there's suddenly column here with the max for 1 million, for example, you can probably think, okay, that's probably something wrong in the data. So you usually also graph this stuff and all kinds of investigations that you do to really make certain that you have the right kind of data. Yeah, I get a question here, if I apply any weights based on country size. Not yet, but I'm going to do that. So you saw just a while back that there is a population data figure in here as well. Here I'm just doing basic checks on reliability of the data, you might say. So there's lots more that you can do, obviously, but yeah, these are just some examples of what you typically do. Yeah, and then it's time for visualization. So most of the time you start drawing graphs as soon as possible because you can summarize a lot of data in a graph. Obviously, you can have start making sense of what's going on here. So yeah, if you have your data in a format like I just described, it becomes very easy to start plotting it because if you want the cases for the Netherlands, you just select cases for the Netherlands and you do a plot here. So I already see India mentioned here. So if you want India, you just change this into India and run the cell. And this is India. As I mentioned, this data set only has data until December. So this is not the current data. But yeah, we'll see that later on. But at least you can see how easy it becomes to start selecting countries here. So if you want the UK, you just fill in UK here and you start getting the results for that. Oh, that was the wrong button. There you go. So this is, for example, the UK. So yeah, if you start doing this to get to know the data, you basically also start getting. Oh, did I think I just said UK there. Hang on, I pressed the wrong selection, I guess. Yeah, there. So this is the UK. I was thinking this should look different. I've been looking at these graphs for so many times that I already start recognizing countries by their graphs. So that's something really going wrong here. But anyway, so this is the UK. So there's a couple of things you can see here. If you start comparing countries, you can see that in most of the countries, this first outbreak, let's say the period from March to July, the first couple of months of the outbreak, look pretty similar. It's a steep rise, then you have something of a plateau, and then then it goes down slowly again. And then afterwards, there's lots of second outbreaks and overlapping and multiple and whatever. But for most of these countries, and I was starting to look at this stuff in April last year, so I only had the rise for most of those countries. I already started to see some similarity, at least in the shape of the curve. At the same time, everybody started saying, yeah, we need to flatten this curve. Why do we need to flatten this curve? Because at the top of the curve, there is a lot of people that are infected at the same time. And it's typical that if there's a lot of people infected, then a percentage of that has to be hospitalized and another percentage of that ends up in the IC, the intensive care unit. And that is the real problem that we needed to tackle at that time, that every country has a fixed ICU capacity. I mean, there's just not more available. And that's usually not the amount of beds or the amount of ventilators that they have. That can also be a problem, but it's usually a problem of the amount of nurses available to care for these people in an ICU environment. So that is the first limit that you get into when you have this kind of disease outbreak, just the capacity of the healthcare system to handle the disease. So that is the first thing I started concentrating on. I noticed that in this first outbreak we had similar shapes in the outbreak. And I wanted to say something about the maximum amount, the maximum load on the healthcare system, and if we could, in some way, understand what was going on and maybe even take measures to alleviate that, to actually flatten that curve. But yeah, then you first have to understand the curve. Before you get to that, there's some other problems that you have to solve. You can already see it very clearly in this graph from the UK. That you're never measuring what's actually going on in the real world. There's always a measuring process going on. So you have these people getting infected. Then you have this test that you take, which also has its advantages and disadvantages. And then there's also a reporting process going on. So you're never looking directly at the amount of infected people. You're always looking through the tunnel, you might say, of the reporting process. So what's going on here, for example, which is very clearly for just about every country that reports its figures, that there's a weekly effect going on here. So I also ran the analysis to find out what was going on. And typically for just about every country, the figures for Tuesdays are the highest figures of the week. And that is simply just a reporting process. So what you see is that the cases that get infected on Saturdays and Sundays are usually reported on Tuesdays. So every Tuesday or maybe Wednesday, if the Monday is a bank holiday, you actually do see that effect. You get the peak in reporting figures. So if you just take this data and start predicting stuff, it's simply the models that you will use will typically just say next Tuesday will be another peak. And that's true because that's what you see here, but it doesn't help you very much. So you have to take out this reporting effect to actually try to make sense of the actual figures that are before the reporting process. So this is just something that is introduced by the way that these figures are reported. That's just the investigation that you have to do. I mean, you see this graph, you say, that's weird. Why are the Tuesdays always higher? And then you look at, well, this was in the press already, so that was pretty easy. But I talked to a lot of virologists and epidemiologists. I even learned to pronounce epidemiology without tripping over all those syllables. I talked to a lot of those people during the year to make sense of what was going on. This is what I'm looking at, but what is behind this? Why are these figures the way that they are? And there you see a lot of other weird peaks that are going on. And if you look at other countries, like a typical example is Ecuador, for example, you even see something that you don't understand at all when you start looking at this. So these are the reported figures for Ecuador, for example. They had, for example, a lot of people that got tested positive, but there was no date attached to those tests. So suddenly, somewhere in May, they said, "Yeah, we've still got, let's say, 11,000 people here, and they got infected, but we don't know when. So let's just report them on one day." That's a typical example where you say, "Okay, obviously these people, there were no 11,000 people infected on that day." You have to deal with that if you want to make sense of the figures for a country like Ecuador. You have to think of what to do with those. You could spread them over the weeks before, maybe. You could take them out and just say, okay, I'm going to ignore those 11,000 people, but then your totals don't match up anymore. So you have to make sense of that. And even worse, they said after a while, we reported those 11,000 people in May, but after we still think that about 2,500 of them were no COVID cases after all. So we're just going to report another day in May of negative figures. We're just going to subtract them. So the totals are still correct, but we actually have a negative amount of cases on this date in May. And after a while of reporting, and you see a very strong reporting effect here with the numbers going up and down all the time. In September, they said, we've still got these 7,500 people that we're just not sure if there were COVID cases after all. So we're just going to subtract them. So then you get suddenly something like a negative amount of cases again, which is something you have to deal with. And obviously, if you are fitting a curve to this, you will get a very weird curve, and you will never be able to make sense of, did they actually flatten the curve there? Because there is no curve to look at if you look at this kind of data. There's a lot of stuff in the cells below and in the stuff below going on in taking out those kind of measures. And actually, what is very interesting when you use this kind of data, which you will see all the time. I mean, I also worked a lot with process data, whereas with temperature data from a process, for example. And that's one of the things you could also apply this kind of analysis to when you're starting your call for code project on climate change. You could start looking at sea levels or temperature data in this way. But you will always find out that there will be weird stuff going on. I also had negative temperature suddenly from a country where it was 30 degrees outside all the time. And suddenly one of the sensors reported 5 degrees below zero, for example. That was just a faulty sensor. I mean, that's what happens. So you have to deal with that in some way. And that can then from the data, you first have to take out these problems, the reporting, the process problems, before you can actually use that temperature data in any sensible way. So if you just take the average measurement of temperatures in that case, and you don't look at the detailed data, they will be a lot lower than you would expect, because you had a faulty sensor a lot of the time, which reported negative temperatures. So yeah, you always have to dive in and find out what's going on, and then think, how do I deal with that? And you can deal with that in two ways, basically, two main ways. There's lots of other ways, but two main ways. You can either leave it in and test your analysis process in how it would deal with this kind of weird data. So you can try curve fitting after all on this kind of data and see what comes out, if your curve fitting approach is robust to this kind of problems. But it's an interesting test. But then you find out more about your own analysis process than about the data. So you have to think that you are working with faulty data and just testing your analysis process. And the second approach, obviously, after that, most of the time, is to take out that kind of weird data and then really find out what's going on. But what I usually do first run is just leave it in and see what happens, and see what happens to the analysis process, and then find out if it's really a problem. Take it out and then run the analysis for real. Basically, that's the way that you can approach using this kind of data. So yeah, it's because I had these two slices of data now. You can also easily look at the depth figures, which is the same kind of statement, and you can see that the reporting effect there is even stronger. There's even more of a reporting bias here than in the case data. So here you have to take corrections for sure. Basically, I mean that's you just cannot deal with this kind of well, let's say messy data. So you there's quite some investigation going on. But yeah, feel free. It is as simple as starting in a Python analysis environment, which you can do for free in the IBM cloud, or you can run it on your own system. Start up this notebook. It downloads its own data, and just have a look at countries, effects, and stuff here. It shouldn't be hard to run this first notebook. The next ones will be more complicated properly, but you can combine data, so you can easily do case data and death data in one plot. So there's quite some examples here. China had this big reporting problem here in February already, where they had 15,000 cases without a date. So there's another one of those interesting peaks. And here you can see, probably if you want to analyze this curve below here, you'll probably just take out this peak, and you're left with a curve that you can probably make sense of. But that's a choice you have to make. Always check if this data is for real. If it's not a problem in my analysis, could be that I did my pivot in the wrong way, and that's why this weird peak is here. So I always check in the original data if that peak is actually there. It is there. There's the 15,141 cases that were originally reported there. And then it's just, I started reproducing most of the graphs that I saw in the press and in the documentation and in the papers that were coming out at the time. So there's stuff in here like a cumulative graph, where you start adding all the figures, and you can see how the cases are rising in several countries. Then you can start comparing. For example, you see that China was early, the Netherlands were after that. In this kind of graph, you can't even see the amount of cases in New Zealand because it's so much less. And you can see already that we had a slow rise here in the Netherlands, and then really the cases started taking off, for example. While in China, we just had this first outbreak, and then not much additionally was reported. There's a slight rise here in August last year, but not much going on there. But again, this is reported figures, so deal with that in the way that you see fit. Just keep in mind, it's what the country reports. That might not be what is actually going on, but that goes for every country. I mean, that's not to pick out a country in any way. That's what happens everywhere. That's usually the reporting process is dirty in some way. Not always intentionally. There's just stuff creeping into the reporting process. You get these logarithmic plots that you saw a lot in the beginning. Maybe you recognize them from the plots that you see. So here's a very easy way to make them yourself. Some examples. So that's pretty easy, and then you can very easily compare countries, because if you do a logarithmic plot, then the differences are much less. because then, yeah, one tick on the axis here doesn't mean that it's one more, but it means it's 10 times as much. So you can start comparing countries and see where they really started rising, when the outbreak started to flatten. So there's lots of examples there. And you see this effect in a lot of countries here. For example, at the bottom, where you did this first outbreak, more or less, is probably what I found out in a lot of discussion, people traveling into the country. So they're starting the outbreak, basically, and then the rest of the country takes off. That's what you see in a lot of countries. So there's always this first smaller rise, then a little bit of a plateau, which most of the time is more or less the incubation time of COVID. So that's making sense here to use that term. This is it takes a while for the first people to get infected by people coming from outside the country, and then it usually takes off. So this is the first, making sense of what's going on by tying this period here to the incubation period of this disease that we're looking at. And that's a specific period for diseases. For COVID is typically somewhere between 1 or 2 weeks, somewhere around 10 days. That when you get in touch with somebody, you actually get infected. Lots of other graphs. I won't go into all of them. Some very interesting examples of this reporting process to take out, and then the first examples of smoothing that out a little bit. So it's pretty easy when you take this selection. So for here I got the cases for Belgium and the Netherlands in this case. You can take a rolling mean. That's what actually you just add in your statement after the data set. This means that I'll always take the average of the 7 days before today. And you can understand if I specifically took these 7 days, because every 7 days you have this peak. So if I take the 7 days average moving window over the data, I always have one of those peaks in my window that I'm looking at. So that smoothed out the graph pretty much. And specifically for this 7-day reporting effect with all the peaks every week, you take that out. You just take the average over 7 days, and you lose some of the detail, obviously, but it very nicely takes out this reporting effect, which you can see in the graphs, because now you have something that looks a lot more like the graphs that you see that you saw in the papers, and you have this very much more smooth line of the outbreak data. So this is one of the measures that you take in to compensate for that effect. So I'm always from now on always looking at this weekly moving window, and it's pretty easy to code. I mean, it's just all the methods are available in this Pandas library to do that kind of stuff. You can also see that I only look at data from 1st of March onwards, so it's pretty easy to specify that. So if you only want to look at the data from March to July, for example, it's as simple as just putting a 2020 0701 here, and then I just get the data from March to July. So it's pretty easy to play around with these graphs and select the data that you want to see in the way that you want to see them. So yeah, feel free to experiment around with this kind of stuff. Yeah, you can smooth that smoothing. You can do that even more radical. So for example, here I did a radical amount of smoothing on the China data. So this whole peak that we had on one day is now distributed around the 2 weeks on the 2 weeks around that date. So you can see that even when you have that kind of dirty data, you lose a lot of the details when you start smoothing it this way, but you get something that's maybe recognizable as a kind of curve. So this is one of the things that you can try when you really want to make sense of what was actually going on, is smoothing this data in some way. And yeah, the disadvantage there is you lose the detail because you smooth every number over the 2 weeks around it. So if there was one weird day, yeah, it just gets smoothed out, which is the purpose of this. But on the other hand, if you're looking for a day like that, you won't find it after you smooth it. So yeah, think about what you need for the kind of analysis that you are running. But you can take out a lot of these problems with moving windows, averages, and stuff like that, which is relatively easy if you've done this a couple of times. So here you've got this graph for a couple of countries again. Yeah, and then I really started concentrating on my initial thought, where I said, okay, I more or less understand what's going on here. I can take out the reporting stuff. So let's concentrate back on what I was actually looking at. How many people are concurrently affected at the peak? So how many people are infected at the same time? And a percentage of that is ill, a percentage of that is hospitalized, a percentage of that is coming into the ICU. So that is my starting number, where I say, okay, if I've got this number, how many people are infected, I can probably say something about how heavily the healthcare system was hit in that country. So this is an example of that. In the beginning, when we were just starting out, so I'm plotting data here from March to June for the Netherlands and Belgium. About 8% at that time was hospitalized. So I just simply take the whole graph and I just multiply it by 0.08, and then you get this kind of graph, which pretty much matched the amount of the hospitalization figures. So what I do is I always take, in this case, the sum over a 2-week window, because that is, well, at that time at least, most of the papers described the incubation period, or the time that you are infected, as somewhere around 2 weeks. So if you take the 2-week sum and you slide that over the data, and you take 8% of that, you get the amount of people that are in ICU at that moment. That is what I found from discussions and papers at that time. So now you have that graph that shows you, for every date, it shows you the number of people that are that have to be hospitalized and get into the intensive care unit. I matched that to the figures, obviously. So if you do look at the figures, this matched the figures for that period in Belgium and in the Netherlands pretty well. I already said we may have to gradually lower the percentage. That's what I already said in April or May, because you see that when a disease really progresses, usually, and for COVID it also counts, that percentage of people that get into the ICU gets lower and lower. Because in the beginning, the people that get infected are the most susceptible people, and more of them end up in intensive care. And after a while, that number goes down, luckily, because if it would have stayed at 8%, we would really have been in trouble in these outbreaks. So now it's much less than 8%. But yeah, that's something that I perhaps leave to you to analyze how this figure progressed over time. There is a lot of countries that have hospitalization data available. Then again, that's not available for all countries. So this, at least, if I take this 2-week sum over the data, it at least gives me some kind of number that shows me how heavy is the load on this healthcare system. Because if you then take the top of that, you got the maximum load on the healthcare system. So for every country, if I take this 2 weeks total, and I look at the top of the graph, I have a more or less reliable measure of how heavy is the healthcare system hit in that country. That is the next step that I took. Then I got into trouble, because what actually is the top of this graph? So you can smooth this for a long while, and then you get something that looks like a real top. Here you can see the top. But for many countries, like for the Netherlands in this case, this top and this top is almost as high. So what is the top of this graph, and how many people are infected at that point? To really answer that, you really need to understand how this, what the form of this graph is. What kind of curve are we looking at? And that took quite some discussion and quite some research. There were some early papers that already said, we need to use a Gauss distribution, because that's what usually what's used in this kind of cases. But then, for example, if the Gauss distribution is the typical bell curve that you've probably heard of, which is symmetrical. It rises steeply and has a top and then goes down steeply. But it's symmetrical, and I already could see, and lots of people could see, that for the countries that were already over their top, that it's not a symmetrical curve. It rises steeply and it goes down a lot slower. So there's more people in the second half of the outbreak than in the beginning. That's more or less goes for just about every country that I looked at and discussed. There was quite some research going on, and what I actually found out, because I did a lot of work in predictive maintenance, which may sound weird, I found out that the what we call in statistics a Gumbel distribution is the best representation of that curve that we are all looking at. Well, you can see it visually. You say, okay, yeah, that looks like a disease outbreak curve. And then obviously there needs to be a lot of scientific discussion about, yeah, is this actually what's going on in the real world? Can we use this? How applicable is this? How hard is this to fit? Can I make the story around it to tie this approach to what is actually going on in COVID? Because the Gumbel distribution is usually applied to what we call predictive maintenance. And predictive maintenance is, I do have a lot of experience there, so that helped me in getting into this kind of approach. You usually say, okay, I've got a factory with a couple of machines running, and I've got a couple of factories all over the world where similar machines are running in different circumstances, and all these machines fail after a while. And what you try to do in predictive maintenance is try to predict the moment that a machine running in certain circumstances will fail. That is what you usually do. And there's a lot known about the mathematics around that. And one of the approaches that is used there is the Gumbel distribution. And then I said, yeah, okay, but it looks interesting. It looks more or less like a COVID outbreak curve. But what's the story here? And the story is that you consider not the daily probability of getting infected, but you look at the whole system where you say, okay, I've got these people running around in a society under certain circumstances. And what I see in the infection curve is that a number of days that it takes for somebody to get infected. So you're not looking at the daily chance anymore. You're looking at the distribution of how many days does it typically take for somebody to get infected. And that is more or less similar to analyzing a machine under certain circumstances and looking at the number of days it takes that machine to fail. So that is, yeah, more or less the story behind why you can actually apply this kind of distribution, this field of mathematics to COVID outbreaks. And there was a lot of discussion going on all over the place. And I saw in April, May that the first papers started coming out already, also scientific papers, finding out if a Gumbel distribution would be applicable to this kind of data. At that time, I just said, okay, that's enough of the science, of data science. Now it's back to the data. What you usually do in data science, you look at the science and see if you get something feasible to try as an experiment, and then you go back to the data and you just see if it works. That's what I usually do. So yeah, see if it works. So that's not as easy as it sounds. It means that you take the actual mathematics from the Gumbel distribution. In this case, I won't dive into it too deeply. We can do a separate session on that if you really are interested how that stuff works in detail. But what it basically means is that you try to find out what parameters of the distribution, and in the Gumbel distribution there's just two parameters. What parameters you use as an input to that function so that it has the same shape as the COVID outbreak that you're looking at. And the lucky thing about the Gumbel distribution is that it only has two parameters. One tells you when in time is this function happening, so at what point did the outbreak happen if we tie it to COVID. And the second one, which is the beta value. So the first one is mu, that's the time parameter, and the second one is beta, and beta just tells you how wide is this curve. So basically, if you look at COVID disease outbreaks, beta is more or less your flattening parameter. So if you have a large beta, you have a very wide flat curve. And if you have a low beta, you have a very steep small curve. So actually, flattening the curve in mathematical terms would actually mean here, try to lower the beta. That's basically what you're trying to do. And I approach it the other way around in saying, okay, I've got this outbreak data. What is the mu and the beta? If you look at that data, can I calculate that in any way? And then you can start comparing betas and see if a country was better or worse in flattening the curve, basically. Yeah, that's a bit of a long story. It is complicated. It actually took me, I guess, 1 or 2 months of equations and science and trying out stuff. to implement this, because that is a pretty complex part of what we're looking at right now. But yeah, in the end, I managed to do that. So that's the second notebook that we were looking at today, which is a bit more complex to understand. On the other hand, if you don't really want to understand all the underlying mathematics, you can again fill in the country and see how it works for that country. We will look at the practice of if you found something out like that, how do you implement that? So again, this is the curve for the Netherlands from until June. So basically the first major outbreak in the Netherlands, which looks more or less like one of the curves that we just looked at. So you might consider this a Gumbel curve. So now we're going to try to fit the curve. And what you do in curve fitting most of the time, if it's possible, you find out what's the formula, and the formula is here. It's basically, it's not that complex. It might look complex, but it's this one, where you say this is just a line. So this is a linear function. So it's just a line, linear relationship between points, and then it's just a double exponent. So it's just if you remember some of your high school math, it's just e to the power of that line, and then again e to the power of that. So if you turn that around and you say, okay, I've got this kind of function, how am I going to fit data to it? You could take the double logarithm, then you take out these two e factors, and you should have a line. So basically that's what we try to do here. We say we take the double logarithm of this data, of this graph, and if our considerations are correct, we should have something that looks like a line. That's basically what we're going to test here. So that's what's going on. So here I define these Gumbel functions. There's a lot of stuff going on in data cleanup. Here I cleaned up the graph to look like the cumulative graph that we use to describe the function. Then I reduce that to something that goes between 0 and 1. Because yeah, that's what you have with statistical distributions. They always go between 0 and 1. So there's some code here that tries to scale that back and find out how I can fit this data between 0 and 1. So here you've got the cumulative graph for the Netherlands between 0 and 1. And you can already see that it looks a lot like this cumulative graph that you have for the Gumbel function, which is also this kind of graph. Yeah, so now, as I said, you take the logarithm twice. That's what I do in this little bit of code, and see what you get, and you get a line. So that means that the original assumption that this curve looks like a Gumbel distribution, yeah, is more or less confirmed, because if you apply that, if you take out the Gumbel function, you are left with a line. Yeah, which is something pretty easy for a data scientist. If you have a line, you can simply do linear regression and fit a line to that. And that line that you fit to it has two parameters, again, similar to the Gumbel distribution. It has a intercept, which says how high is the line in the graph, and it has a slope, how steep is the line. And you can translate that with a bit of mathematics to the mu and the beta of the Gumbel function. So that's what's going on here. I've now got a line. And then again, if you have a line fitted to the data, you take the exponent twice, and you should have something like a curve that looks like your data. So again, you first reduce to a line, you fit a function to that, and then you calculate back to the original data, which is what's happening here. So I calculate my beta and my mu here. So that's actually what's going on in the code here. We don't have enough time to really go into the details, but okay, I convert this line to back to the curve that goes with that line. This is a little bit of formatting to plot it in the right way. And here's the first result. So here you got the cumulative function. And let's look at the daily figures if we derive it from there. And this is then the result for the curve fitting for the Netherlands. So what do you see here? The blue data is the original raw data. So again, this very strong reporting effect. The orange line, I hope you can see that correctly. The orange line here is the smooth version. So that's what we are actually trying to fit our data to. And then the green one is the calculated line. So with all my assumptions of this being a Gumbel function, I found out that you can indeed very well fit that kind of function to a disease outbreak that you have. So you might wonder, why did we all do this? Because I already had something that looked like a curve, and I had a top here. Because I now have a description of this data with actually a very simple function. So now if you want to know where exactly is the top and how high is it, you can simply take the mathematics, and you don't have to look at the data anymore. You can simply take the equation that you now have for this curve, which is a very nice smooth equation, the green line, and you can simply calculate how many people are infected at this point and how high is this point. So to summarize, after some mathematics, which is pretty usual in data science, to take a step out to a bit of mathematics and curve fitting, I now have a description of a COVID outbreak. And I can do that for just about any country. So if we look at the UK, for example, then I have to go back a little bit. There's quite some calculations going on. I can simply go back here and say, okay, let me have this for the UK. And I can run everything below here, and it will step through all this stuff that I just described roughly. Oh, and I'll hang on, jumped down a little bit. So for example, here you have the same stuff for the UK. So again, blue is raw data, orange is smooth data, and the green one shows you the fitted curve. So that's actually the description of the first outbreak in the UK. Anyway, so now we have a description. So what we can do now is we can, if we take the data from this first outbreak for every country, we can now describe that. We can now make sense of what's going on. We can simply have a calculation that tells you what's going on. And for example, if you look at the UK data, I fit this line, this green line, only based on the orange data, which stops here in June. So I did this analysis already in May, for example, and you can see what's the advantage of having a line fitted, because it simply extends into the future. So what you can now do, even for countries where you are still in the rising part, if you can fit this curve to it, you can describe the full progress of the outbreak in that country. So you can already, when you start nearing the top, you can start, if you can fit this curve, you can start predicting when the top will be and how high it will be. So that is very interesting, that you have now some kind of model of the specific outbreak in a country, which you can use to extend it into the future. It never works very far into the future, obviously, because you can already see that in the UK, that this is the downgoing slope of the original major outbreak, and obviously there will be secondary outbreaks. So it never goes down as quickly as you would predict for that specific outbreak. Because there will be outbreaks in other parts of the country, and you can already see that here, that the UK figures here after June start breaking out of the first prediction, which is normal. And I've done a lot of stuff in next outbreaks and stuff which we will only look at today a little bit. But yeah, of course, there will be more than just this first outbreak. But at least we found a way to describe that, and we can start looking at other countries. So yeah, you can look at other countries individually. But obviously, I made this second notebook that is called Gumball Multi, where I put all the code from this first notebook, where I can make sense of this first outbreak, simply into a loop, which is in Python pretty easy. You just do a for country in countries around that whole block of code, and it will do this calculation for all the countries in the data set. That's what's going on here. So the code here is the same as in the previous one. It's just one block, and it gets repeated for all the countries. So if you run that, what I actually do is I try to get that figure, the top of the curve, and the amount of people infected at that top. I try to calculate that for all the countries that are available, so I can start comparing them in the end. And yes, I will use the population data there as well. You will see that I start using that relative to the amount of people in the country, obviously, because yeah, that gives you a measure of what's actually going on. So the output of that whole loop is just for every country, and you see it starts with Andorra again, because that's the first country in the data set, AD, and it outputs all this stuff, which look pretty technical, but basically what it does, it outputs the beta and the mu for that country. So that this is that flattening parameters. So you can see that in Andorra, they had a very small, tight outbreak, while, for example, in the Arab Emirates, that had a much higher beta, which means a much more flattened curve, for example. So you can already start seeing differences here. The mu is just the point in time, which is days after the January 1st. So the top for Andorra was 91 days in the last year. So that's somewhere in 1st of April. And the outbreak in the Arab Emirates, for example, was much later in the year, after 133 days. So that's actually the parameters here. And I actually calculate a couple of those dates from because I do have the equation for the curve now. So I look when does it start? When does it start taking off? When was the peak? So what's the peak date, which is indeed 31st of March for Andorra. And when did it flatten out? So when's the floor? When is it getting near zero again? So that's a couple of the dates that I output, which I can use in my further analysis. I've got an idea of how flattened the curve is. I've got an idea when it was. And I also do some confidence figures. So I was very well able to fit the Andorra data to the curve. If this number is 1, it's perfect, which is never the case. So for example, you can see for AI, and I can't remember what country that was almost a perfect fit to this Gumbel curve. So high numbers here mean that I'm actually making some sense of the data. It actually fits my approach pretty well. And the percentage here, which is this column, actually shows you where this country is in the progress of this curve. So, for example, at the point where I looked, Andorra was already way over the first curve, already at 114%, while in Afghanistan, for example, things were just starting. It was just at 18%, so it was really in the beginning of the outbreak at that point. So that's the percentage figures that you see here. So yeah, what I do is from all that basic daily infection data, I generate this data set, which for every country gives you an idea of how bad is the outbreak in that country and when did it happen. That's basically what's going on here, which is quite some data manipulation, but yeah, that's what we do in data science, I guess. So yeah, all the countries are here. So have a look at your own country. But keep in mind that this is the analysis for the first outbreak. It's not the recent data. I looked at a lot of that afterwards, but for now we're just looking at the first major outbreak because that was the panic at the time. Let's put it that way. So this is actually what I output from this, and you can see, for example, that the population data is in there as well. So if I get an idea of how many people are infected at that top of the curve, I can relate that to the amount of people actually in the country. So how hard is the country hit if I take the country as a unit later on. So you can see that, yeah, making sense is looking a lot at the data, testing a lot of assumptions, but also a lot of discussion with the experts. It's always extremely important to keep the experts in the loop and discuss this kind of data and say, okay, I'm now talking to somebody who knows these countries, for example, who knows the UK and the US. Does it make sense that these betas are almost the same for these two countries? Yeah, that's something you discuss with an epidemiologist, and he will probably say, he or she will probably say, yeah, these were comparable outbreaks in the amount of flattening, for example. So that is something that you always not just verify in the data, but also verify with the experts. Because if you don't verify at this point, they probably won't believe you when you come with your final results. So you always keep the experts in the loop. Which can be quite annoying because they come with all kinds of other ideas and they say, yeah, no, this can't be right, and you have to test further assumptions and stuff like that. But it's essential, of course, to keep the experts in the loop. Yeah, otherwise your results probably won't make sense to them. So that's pretty important. Yeah, so a lot of looking at data again. And what I do at the end is, okay, I've created all this data. So I've now got a data set for every country. I've got this line describing what happened in the first outbreak in that country. And I'm just outputting that to a data set. So basically what this notebook does as a whole is it takes in the detailed data and it outputs a new data set, making some sense of what actually happened in the details for that country. So this is, yeah, a typical example of, I guess, a making sense of measures kind of notebook. You can simply run it when new data comes in. If you have new detailed data, you simply run this notebook and you have an output of the current situation for that country. That is what's going on here. So yeah, easy to automate. This is the typical kind of notebook that you just daily run. When new figures come in, you just run it and you got the current situation. Right. So now we've got a measure for every country, basically. So if we can use this figure that I created, which is the maximum current infected. So that's the amount of people infected at the top of the curve for that country. And that is more or less a healthcare crisis measure, you might say. And you can see huge differences there, especially when you relate that to the population data. So that's what we're going to do now. And try to make sense of why are these measures different, because you see big differences between countries if you look at it from a relative point of view. So that's what's happening in the next, and for today, probably final notebook. There's many more, but this is what we are looking at today. We're actually trying to find out if there is what the differences are between countries. So do we see big differences? And can we make sense of the differences? Can we tie that in any way to the actual measures that were taken in the country? So that's always the confusing thing when you're talking about measures. Now we're going to look at country measures like lockdowns, masking, healthcare measures, that kind of stuff. And we're going to try to relate that to what actually happened in the country. So there was a lot of stuff going on now in making a measure of what is going on, and we're now trying to relate that to what happened there. Can we make sense of that relationship? So this basically, what this notebook does, it loads in a data set, which is a very useful data set that I found at acaps.org. I'll just show you the website. And what ACAPS does, it's a non-profit organization which basically gathers situational data, humanitarian data that they call it. They gather situational data for just about every crisis and what's going on in the world. So what they did for COVID is they made a data set where they said, okay, in this country, on this date, this kind of measure was taken. And a measure is then, for example, we started a lockdown at that date. So this is a group of people that actually, from all kinds of sources, so that might be reported, automated sources from countries, but they also look at government sites and stuff like that, and they try to compile from that a daily data set that shows you everything that was going on in that country at that time. So yeah, that would be a very useful data set to use in my analysis, because if I can relate the dates that things were, that measures were taken in a country. So for example, they started the lockdown at a certain date. Yeah, perhaps I can relate that to the severity of the outbreak. That is my assumption for now that I want to test. So I found this data set. There's others as well. For example, Oxford University in the UK also compiles a data set with stringency indexes that they call them, which basically tells you on a daily basis how stringent the measures were in a certain country. So were they in a strict lockdown or not? Was there masking in that country? Were there economic measures taken and stuff like that? So there's other data sets, but well, at least as a starting point, this one is very useful in this kind of analyses. So that's the data set I'm reading in here. So again, you can simply run this notebook. What it will do is it will read in the data set that was produced by the previous analysis, the severity of the outbreak for every country, and it will also read in this data set from ACAPS with the measures that were taken in that country. So this is basically what's going on in this first cell. So here I read in my own data set that I produced just before. So again, just just a test to look if that got read in correctly. So I've got all my data that I need for the analysis. Yeah, and what's going on here is what I do is actually the maximum current infected. I divide that by the population data. So here's your relative measure. Looking at country size, I say, okay, so many people were concurrently infected at the top of the first outbreak, and I divide it by the population data to get a kind of relative measure, so I can start comparing countries. Then there's the first plot. So here you've got the output of the previous data set, more or less, but then relative for the country. So how heavy was that country hit by the first outbreak, basically, is what's going on here. These are logarithmic measures, so again, maybe a bit complicated. So if it says -3 here, that means that 1 in 1,000 people for that country were infected at the top of the outbreak. If it says -2, then 1 in 100 people were concurrently infected. If it says -1, then 1 in 10 people were concurrently infected. Luckily, we don't have any of those. But we do have, for example, Qatar, which had a very heavy outbreak in the beginning. And you can see that almost 1 in 1,000 people there were at the same time infected in the first outbreak. So they were very heavily hit by the first outbreak. Here's, for example, Andorra again. And you can, I ranked the first countries that were over 1 in 1,000 people. And you can see, for example, here's the UK, here's Italy. So you can see, you can start seeing differences between the countries. And I tested, of course, this graph against the news from that countries, what I found on websites, what I found about descriptions of those countries. And this is a pretty good measure of how heavy the country was hit in the first outbreak. So this is a way of measuring that. So again, I look at the maximum amount of people concurrently affected at the top, relative to the population of the country. So which part of the country was infected, you might say. So there's some well-known in here. Of course, you also get some weird stuff like the Vatican. You say, yeah, how heavily can the Vatican be hit? But yeah, there are only 1,000 people living in the Vatican, registered as Vatican residents. And at a certain point, there were 7 infected at the same time. So 7 in 1,000. Obviously is a very high figure. If you would have that in the UK, you would have a big problem. Of course, for the Vatican, that was not that big a problem because they could get those people into hospitals in Italy, but 7 in 1,000 is a large number. So you always see a couple of smaller countries, very high and very low in your data set. Yeah, well, simply just because they are statistical anomalies. That's only a small amount of people. So yeah, that's why the Vatican is here, for example. But yeah, so I've got my measure. I've got my severity measure, which is amount of people infected relative to the country size. So yeah, that's going to be the target of my analysis. Doing some testing here to see what the actual figures are. You can see that for some countries it's -2, which means almost 1 in 100. That's a huge figure. But for other countries, the minimum amount is -5, which means 1 in 100,000, or 1 with 5 zeros. So there were some countries that were hardly hit by the first outbreak. So this number goes anywhere between 1 in 100 and 1 in 100,000 people. That's basically what you see in the results here. Then I read in this measures data set, government measures, I should say, to keep it clear. And here you see some examples of what's in that data set. So for example, you've got a type, so you can see if it's an introduction or if it's a phase out of measures. So that's what's logged in that data set. There's a category there, so you can see there were public health measures taken, or there were social distancing measures taken. There's even more details there. So the social distancing measure taken in Zimbabwe on, what was the date? July 28 was a social distancing measure, and it actually was a school's closure. So there's very much detail in this data set. Yeah, which is an open data set. You can simply download it, and it tells you exactly when, in which countries, what kind of measure was taken, basically. So it is a pretty large data set. There's very much detail in here. There's even comments here. It tells you where it was found. There's even a link to the original message where this measure was announced. So for Zimbabwe, this measure was announced on Twitter. This one is on an official website. There's stuff being taken from Facebook. It's all over the place, but it's compiled into a very neat data set in this case. So for now, for this analysis, I'm only going to use an introduction of measures. So I filter my data set by just taking only the introduction of measures. Obviously, when you're looking farther ahead in time, you also have to start looking at relaxation of measures. It might be that somebody went out of lockdown too early, and that was the cause for a very heavy outbreak. But for now, for this first analysis, I only look at the introduction of measures. So feel free to extend on that. So what I try to do is I take these two data sets together, and what I want to see if I look at the start of the outbreak in a country, I want to relate that to the dates that measures were taken. So what I'm calculating in these next couple of cells, which is actually what you see happening here. What I do here is I take the implemented date for a measure and I subtract the start date of the outbreak for that country. So I get a kind of relative number that says, for example, the outbreak in the UK started on this date and a lockdown measure was taken a certain amount of days before or after the start of the outbreak. So I'm trying to relate how early or how late certain measures were taken to the start of the outbreak. So how did the government react to the outbreak, basically? So did they already start taking measures before? Then I get a negative number. So I can get a negative number of -10 that would tell you that a measure was taken 10 days before the actual start of the outbreak. So they were very careful in that country. But you will also see positive numbers that tell you, okay, a lockdown was only taken maybe a month after the outbreak. So that's the kind of number we're looking for here. So I tie these data sets together and I simply calculate the difference in those dates. And here again, you can see that some of the measures were already taken 132 days before something actually happened in that country. So there's a couple of African countries, for example, that didn't wait for COVID to appear, but they already started taking measures just to prevent it from coming in. On the other hand, you can also see that some of the measures in some countries were only taken 118 days after something happened. So there are some countries that reacted pretty late. And some measures, for some countries, like if you look at Brazil, for example, they hardly took any measures. So even the first measures were taken very late. And that could be as late as 118 days after something actually started in that country. So if you're still with me, we now have a number for how severe is the outbreak. And we have all kinds of numbers for every country that tell you how early or how late were measures taken, measures of a certain category. I'm going to look at the categories indeed. So I'm going to look at the kind of measure that was taken. And if I take all that data together, which is a bit of Python, but have a look at how that works, you get this kind of data set that tells you for every country how early or how late related to the start of the outbreak in that country were certain measures taken. So for example, again, I always look at the last data in the set because the problems are usually at the end of your data set. So for example, if you look at Zimbabwe again, you can see that governance and socio-economic measures like giving support to companies so that the people don't have to get into the company to work there, but they can work from home, for example, or companies that cannot do their work while being in a lockdown, they get support from the government. That's the kind of measures that we're looking at. You see that Zimbabwe already 37 days before the outbreak started taking that kind of measures. So they were actually preparing. And that's, well, more or less a feasible number because you see that Africa was pretty late in COVID outbreaks. Europe and the US and Asia were already quite a bit underway before cases started to appear in Africa. So some of those countries prepared really well. So for example, Zimbabwe, 37 days before the outbreak, they already had measures in place. They did not do a lockdown at all. There's no lockdown data for that country, so they didn't do that. But they did take movement restrictions, public health measures, and social distancing. Social distancing already 50 days before the outbreak. So they really try to prevent stuff from coming into the country. That's basically what you see in these kind of figures. There's also some examples of countries being a little late in their measures. So let's say the UK, for example, they did go into a lockdown, for example, but only 24.5 days on average. There were a couple of lockdown measures which are averaged together. But let's say 3 to 4 weeks after the start of the outbreak in the UK, the first lockdown came about. So yeah, that might have negatively influenced the outbreak there. And all the others were also pretty late in the UK, to be honest. So that is how you can see, what was going on in the countries. So the next thing is trying to relate those two to each other. So how much does being early or late in a lockdown influence the severity of the outbreak? That is the next question. For that, I will use a little bit of machine learning, which is also one of the daily things that you do as a data scientist, obviously. I used a very simple algorithm, simple to use algorithm to have a look at the data. There's some visualizations there as well. But what I used in the analysis is an algorithm that's called XGBoost, which is very well known, used a lot. And one of the main advantages for using XGBoost, which is just a way of relating figures to each other, basically, is that it is very insensitive to all kinds of anomalies in the data. So it's very generally usable, at least as a first model, and it's pretty easy to set up. So what you basically just do is you tell, okay, this is the measure that I'm looking at, which is severity of the outbreak. Calculate a measure. This is my set of data that I want to look at, all the kinds of measures that were taken and how early or how late they were taken. Find out if there's any relationship, basically. That's the machine learning algorithm. I looked at some of the relations already before using XGBoost. This is just the correlation between measures. And you can see, for example, that let's see, one of those examples is humanitarian exemptions for measures were almost always taken together with other measures. They were hardly taken in isolation. So you can see that there's a large correlation, almost one with governance and socioeconomic measures, and almost with all the other measures. So this is not something that you do as a single measure. It's always in combination with others. That's basically what this analysis tells you. For example, a lockdown here, you can see that the lockdown you might say it's not exactly that, but for now, let's put it that way. In 60% of the cases, you take a lockdown together with governance and socioeconomic measures. You don't just only take a lockdown. That's also what this column tells you. And it's very much related also to social distancing, for example. So those measures are more or less taken together. So you might say from this graph, the deeper the color is, how higher the chances that these two measures are taken together and not in isolation. That's basically what this tells you. So this is already also a very interesting graph to discuss with, for example, policymakers or government or health institutes or whatever, which I did. We looked a lot at this kind of data. But this just tells you the relationship between two of them. You can see, okay, is there a relation between lockdown and socioeconomic measures, for example, but where you would like to look at all kinds of combinations of measures, which is what machine learning algorithms do for you, XGBoost in this case. So what I do here, this is a little bit of technical stuff around setting up XGBoost. This is just a control graph for XGBoost, which tries to prevent overfitting. Overfitting is a session in itself, I would say. Basically what it means is you don't want your model to only describe this data set. You want your model to be generally applicable also for new data that it hasn't seen before. Because you can very exactly describe this data set, but it will only tell you what was going on at this point. If you want to make a prediction for a country which you haven't seen before or where there's no outbreak yet, you want your model to be generally applicable. And this is just a control graph that tells you, is this model generally applicable, or does it just describe this data set? That's one of the checks that you as a data scientist always do. And basically, if you don't know anything about these graphs and overfitting, these lines should be almost overlapping. If they are too different, then your model is totally fixed on this data set, and it won't be able to tell you anything about new data coming in. So this is just a check graph going on. But you can experiment with the parameters above here. For example, if you put your gamma, which is a generalization factor, if you put that much higher, you will see that this graph doesn't work for you anymore. So then the model isn't generally applicable anymore. You don't do general statements with it. It only describes exactly what you see in the data set. So that's just some check graphs, and then I create a model which describes the data set. And the first thing that comes out of it is a feature importance graph, which tells you what are the factors in the data that influence the severity of the outbreak more or less. So you can see that public health measures, which is very high in this graph, has a very high influence on the severity of the outbreak in a country. And as I said, and the way that I calculated this is how early are the public health measures. So you can see how early or how late the public health measures are taken, and public health measures are availability of hospitals, but also isolation and stuff like that. So really trying to prevent this from spreading directly. These kind of measures are pretty important for the severity of the outbreak. You can see that governance and socioeconomic measures are pretty important. Social distancing is pretty important. And the surprising thing is that lockdown is way down on this list. That doesn't mean that lockdown in itself isn't important or doesn't do much, but you always have to read this graph from top to bottom. So if you are already doing public health measures and governance and socioeconomic measures and social distancing, then a lockdown on top of that doesn't help very much. It still helps, there's still an influence, but it doesn't help you if you are already taking these other measures. That's basically what this is telling you here. So no general statements about the usefulness of lockdowns here. But yeah, if you see that people in countries where the public health measures are taken and governance and socioeconomic measures are taken are already for much of the time behaving as if they are in a lockdown. So doing an official lockdown measure helps a bit more, but maybe not as much as you expect it to be. So that's one of the things that you would very much like to discuss with policymakers, obviously. And you see then if movement restrictions, even on top of that, don't help that much anymore. And yeah, humanitarian exemptions are not meant to influence the outbreak. They are just humanitarian exemptions. I mean, that's not something that should influence the outbreak. Perhaps in a negative way, it might influence, but the influence isn't that big. So I would almost say you can afford humanitarian exemptions as a country. So still do the right thing because it won't influence the severity of your outbreak very much. That is basically what this is telling you. So yeah, this is a first look at understanding how these measures work and how they influence the severity of the outbreak. But that's all very nice, but you usually need a bit more of an explanation here. So that's there luckily is a very interesting analysis library for that, which is called SHAP. I always forget what it stands for, but have a look at SHAP. And what it can create for you is these very interesting graphs that actually show you for a specific country how much the measures in that country, in this case, influenced the severity of the outbreak. So for example, we're looking at the Netherlands here. So we can look at other countries as well. Looking at the Netherlands here, and here you can say, this is actually the number for the Netherlands. So let's say -3 again was 1 in 1,000 and -4 is 1 in 10,000. So we're somewhere in between for the first outbreak. And these are actually the figures that have influenced this number. On the blue side are factors that actually made this number lower than expected. And on the left, on the red side, are actually factors that made this number higher than expected compared to all the other countries in the data set, that is. So you see that the fact that we took in the Netherlands public health measures only after 37 days after the start of the outbreak made our number a lot higher. So we should have done that earlier, basically. That's what it tells you. On the other hand, the fact that we already 10 days after the first outbreak started, we already took governance and socioeconomic measures, which is 10 days after the outbreak, but it is better than average. That's what you can read from here. It actually made our number lower than expected. So this was a positive influence. So if you look at the Netherlands in this case, you say, okay, we should have done public health measures earlier. So again, you can derive from that the general statement that early public health measures help you a lot. We could have done social distancing earlier. We did not do any formal lockdown in the first outbreak, that is, but that wasn't that negative. So people were probably already more or less behaving like they were in a lockdown because that wasn't that negative of a factor. Early governance measures helped. Early movement restrictions also helped. So that were the positive factors for the Netherlands. So yeah, you can start analyzing all kinds of countries. So if you look at the UK, for example, and you look at this output graph, now unluckily, there were not many factors in the UK that made this number lower, but there were a couple that made it higher. And the main was being late in governance and socioeconomic measures. That is the effect that you tell an organization doesn't get any support from the government, and they still have to keep on working in unsafe circumstances, for example. That is the kind of thing that you're looking at here. Relatively late in public health measures, relatively late in social distancing, relatively late in lockdown. This was really not a good first reaction for the UK. So that is something that you find out from this kind of data. And if you look at my favorite African country in the first outbreak, which is Togo, which had a very low number in the outbreak. And why was that number so low? -4 in this case. It was so low because they took very early public health measures, 53 days before the outbreak, very early governance measures, very early social distancing, very early into lockdown. So that helped really. In this country, in this case, I always have to say, of course, in this outbreak, it helped this country to make their number a lot lower than expected. That is what you can clearly see from this kind of analysis. Any questions about that? Any favorite countries that you want to have a look at? And we are already over the top of the hour, so I'm not sure how long I can go on. I wasn't planning on going on very much longer, so I'm almost at the end of this. So so don't worry.
I did just share the link there for all the GitLab information that you did post on here. But yeah, if you have any questions to the audience, if anyone has anything to post, Bente, I see your microphone's off.
Oh, I just wanted to see India.
Okay, sure. Yeah, but remember that we're just looking at the first period. So I'm not sure if I have anything useful for India, because you should really look at the major second outbreak in India, but we can have a look. Yeah, for the India, and that's clear in the first outbreak, which is basically somewhere between March and July last year, India wasn't hit very hard. And that was, at that time, their numbers were pretty low. Because they took their measures very much in time. And the sad thing about India is they just, when the second major outbreak started there, they just could not afford to take all these measures again. I mean, they just could not afford to do another round of long-term public health measures, social distancing, governance and socioeconomic measures. They just could not afford that in the second. But through the first major outbreak worldwide, basically, they still could, and it helped them a lot. Otherwise, they would have been very much earlier in a major outbreak of the disease. So remember that we're only looking at the first outbreak period. Let's put it that way, from March to July. In that period, India did pretty well, and they could keep the numbers very low, relatively. Yeah, but sadly, they just could not afford to do that a second time. The country would have gone bankrupt probably if they did it a second time. So that's pretty sad when you look at the second period for India, which I don't have at hand right now. But if you want to take the code, adapt some of the dates, and you'll probably be able to look at that period for India.
Okay, well, if there are no immediate questions, I think, Damiaan, it's probably worthwhile for us to wrap up here.
I guess so, yep.
Thank you so very much. It's great to actually see some of the the code, the thought, the processes that goes behind everything that we've been kind of bombarded by the media the last year. To actually put it in such a thought-worthy and step-by-step process, it's been really insightful. So thank you very much for your expertise, your time, and for sharing this information and code with us as well.
Yeah, I'm glad to. So yeah, again, I guess by now you know where to find this stuff, and yeah, go ahead, have a look if you can get it up and running for yourself. Maybe even on other kinds of data. Be aware that the applying such a curve fit doesn't automatically work for other kinds of data. I'm not saying that you could do temperature data with it. You probably could, but you should be very careful with that. Yeah, but if you try to get it up and running for your own environment, and let me know if you have any questions.